Hi everyone, welcome to another Common Lisp study group. I'm your host Ron Batum with Atlanta Functional Programming. Uh, in today's discussion, we're going to finish up problem 7 1 of the exercises. This is the last exercise in chapter 7 in our ongoing series of paradigms of artificial intelligence programming. For those of you who are just joining us, actually, this is not problem 7 1, sorry, problem 7 2. Up until recently, we have been covering the student word problem solver. I encourage you to go to past episodes to get an overview of what this problem solver does. We actually went through a couple exercises of already extending the problem solver. We're finishing up with this one specific one because I thought it was a particularly interesting thing to do. Um, and that is the problem is related to solving systems of linear equations such that you are dealing with two unknown variables, but one can actually be solved by substituting the other. So there would be an equation such as the form, um, and to give you kind of a, a scratch, oh, sorry, not a scratch buffer here. Um, Slide scratch here. We could have an equation of the following, right, 100 equals overhead plus running times 40, and overhead is equal to 10 times running. So, if you're looking at this, you know that you could substitute um, 10 times running for overhead in the above equation, get 50 times overhead, and then divide 50, get running equals 2, which means overhead equals 20, pretty quickly by just looking at the systems of equations. Well, naturally, we want to be able to extend student to be able to do this because up until now, student can only solve the student version that's in Norvik's repository can only solve one type of these equations, where only one known is actually unknown. So to make things easy for us, we're assuming that there will only be two unknowns. And then we could try and see if we could derive a strategy um, with n uh, linear equations and n unknowns. But we will see how far we get today because the last couple of weeks we are actually been investigating just how we might end up tackling this particular problem of solving multiple unknowns. As usual, before I get started, standard announcements. Atlanta Functional Programming is looking for speakers. If you have a topic, anything related to data science or functional programming, or even a particular you know design topic that you want to discuss that integrates some aspect of FP in your favorite language, by all means, please free to reach out to me. I'm Ram Vadim again. I am Bugram on the Atlanta Slack workspace Tech 404, as well as Bugram inside functional programming.slack in the Lisp channels. Plus, I periodically squat. The Lisp Discord server has the same handle, Bugram, too, as well. So, without further ado, let's get back to kind of what we were looking at last week, which was we attempted to create. Our first attack was actually attempting to create, um, we created this version of the problem solver here, so that we can actually go ahead and run um, the equation list that it will generate if we ended up creating this. And we noticed that the first time that we ended up doing this, that the uh, sorry, equations would be of the following. Notice the period being there. That's because of the fact that currently in our student parser, a period indicates the end of a particular equation. So I started using that as a delimiter to actually write out this particular equation. And we noticed that when we actually parse this with the default equation list, we ended up getting the following equation list using the standard create list of equations functions that's already been provided to us by the student program, and that generated this particular equation list. Now, when last time, if you recall, when we attempted to try extending student, what ended up happening was we attempted this one thing of extending the one unknown to see if we can actually create a equation called substitutable. And that kind of is something that we're going to continue working on today. Um, and we created this expression called is substitutable. Um, and we noticed that uh, before we were trying to create different types of is substitutable expressions, but now we had some ability to actually be able to actually encounter this. And we could see that if we end up using this is substitutable expression pair expression p um, on our equation list, first element, we'll see that it's nil, but if we end up calling it on our second one, we see that it's true. Okay. So the nice thing about this is now we have at least some start to be able to actually encounter um, figure out if we can actually substitute um, uh, so this is a substitutable expression. So in this case, we know that left-hand overhead b equals right-hand equation. We know then that we could find, if we could find the left-hand side of a particular substitutable expression's symbol inside of another expression, then we can actually go ahead and substitute the right hand into that. So let's try and do that, and then try running generating the equation list that would actually have the substitutable expressions. I mean, the substituted expression inside the equation. So then what we'd end up doing is we'll end up creating something that will have only one unknown. But there's a couple things to keep in mind when we do this. One is ultimately when we solve the equations, we need to actually grab the variable that has been solved, and we need to go ahead and substitute it back into the original substitutable expression to get the final answer. All right. So there's still a little bit of work ahead of us in order to actually go and encounter this particular thing. Right. Um, so let's try doing something like this. So we know that we have a substitutable expression now, equation. Let's say we want to find a particular equation that contains the symbol and then return it. Um, Now, I'm assuming here that there are only two unknowns, okay? If you're going to do this with multiple unknowns, it would probably be better to um, do this iteratively, and then eventually you'll end up getting into this potential situation where um, either all of the you'll end up into a situation where there's only one equation with one unknown where you could solve it, or it'll end up creating this um, what we call in if you end up using linear algebra to solve this, something that's similar to uh, the minimal set of unknowns that you can actually have to actually solve this system of equations, which is kind of a family of system of linear equations. In linear algebra, you may have heard these terms like row echelon form or reduced row echelon form to actually solving some of this stuff. The row echelon form is kind of what this would end up becoming when you end up reducing it to the point where it can't be reduced any further, but there's still unknowns inside of your systems of linear equations. This would be something that student may not be able to solve, but it will at least give you kind of what we had before, which is, oh, I reduced this level to something or another. I hope, will not have to encounter that when we make this particular assumption that we have two unknowns, and hopefully everything else can solve it um, accordingly. All right. So let's first try to find. Let's create a function called maybe find uh, equation, or we could say EQN with unknown uh, with given unknown. And actually, this might be better if we ended up creating something like, let's say, expers key and we'll call it needle, which is what our search parameter is going to be. Okay, and what we'll do is we have to see if the exper, or it's not necessarily the I guess it is an exper. Let's say symbol. Let's call it symbol. Okay. Um, and what we'll do is for, not for, loop for exper in expers. Actually, it might be better if we do list here, because we don't necessarily need the mini language, because in this situation we're actually looping through the top level expression. So like in this equation list, we are going through, actually, you know what, this will probably be not expers, it'll be equations. Okay. Okay. And what we'll call this is do list EQN EQNS. And inside each of the equation, we're going to have to loop through all the symbols in that given equation. As long as that equation expression is handled correctly, we should be okay. But we will see what would happen if we do it this way. Let's do here loop instead of do list for s in EQN when if it's a symbol p, guess we could do if the symbol p equals s. Oh, we want to do two things. So what we want to do is we want to do if it's a symbol and if it's EQ, I would believe it should be EQ. Let's do a simple string equals to make this easier. String equals symbol name s with symbol name sim. when that happens, then let's return. Can we do return here? Finally. Oh, no. We could just say do, and we will do return EQN. And hopefully that should be good enough. So this is a quadratic time algorithm, but we shall see if this will actually solve our problems. Okay, let's go here. Let's try finding it. Find equation. And it's going to take the first hit by design. So we could do multiple hits, but we're only dealing with the first one each time. Obviously, this will make things slower because we're not actually substituting every one of them. But it at least makes it easier for us to maybe do maybe a functional based one where we substituted, we create a new list. Or if we want to do it destructively, we could use nconc to, or one of the destructive Lisp operations to go modify the particular equation, particularly using substitute, the substitute thing that we used before. So let's go ahead and do this. And let's say that we want to find the symbol overhead. Let's see what happens. Oh, because we made the key argument. That's right. Key, sim, and we end up seeing that it is nil. Why is that the case? Let's go and make sure that what we pass in, print sim. Okay, so oh right, because I'm using if. Oh, I'm dumb. That's right. Else does not exist here. When let's see. Can we do? I mean, another option is to do another do list here, but my feeling is do list will not necessarily work. You know what? Let's try that. I thought that the loop, I thought I recall that the loop mini language had, hold on, I gotta pull up the hyperspec because my loop mini knowledge is, I'm getting forgetful when it comes to what's there and what's not there. If when, I thought there was an if form selectable clause. That's fine while Let's see, maybe let's do loop if example common Lisp. So it looks like what we may need to do, let's see here. You know what? Let's just do that for the time being. We will go through okay. If it, we will return because we need to break from this, so we need to use return explicitly here. Return EQN. Else, let's go ahead and just print the symbol for the time being, just to see if we're iterating through it. Got it. So we found the symbol here. Okay. Let's just make sure. Do this again. Okay. So I'm wondering if we could do a contains here, because Alexandria, if I'm not mistaken, which I have loaded, I believe I do. No, I don't. Okay. Let me go and load up. Now I could obviously write contains in here, but it might be easier. Conjoin. There is. Oh, you could do sub subsequence. Ooh, maybe we could do subsequence. Let me try something. Subseq overhead. Oh, wait. No. We need to make sure that it's a member. Let me see if I could do member overhead ELT equation list 0. Okay. So it's able to at least if it's a flat list, um, it'll just find it. But in this case, it's a nested list structure, so it has to do it recursively. Okay. So now what can we do here to actually accommodate this? We need to naturally think. Let's see. We can actually do so we need to actually go and probably do a recursive check just like before, but I'm assuming that we could check to see if something is an equation and then probably work our way up to that. So let's go ahead and do that. That's probably an easier way of doing it. So do we have a EQN? So what we could do is, let's see. Let's try this other thing. So instead of doing, stringle equals should work, but let's say that it didn't work. Then what we would have to do is check to see if the symbol that we're looking at is itself an expression, right? Let's see, how did we solve this? Because we did something similar for float, I believe. No, we did a. Um, if it's a symbol and the symbol name is the same, then we found an equation that contains the symbol. Now, if it's not a symbol, but if it's a got it. So what we're doing is okay, so let's start this differently. Oh no. Okay. For each equation in equations. Now, let's do let us do the following. Okay. Let us do LHS being the expression's left-hand side, EXP LHS. No, not op, LHS. Okay. And EXP equation. Okay. That's the left-hand side of the equation. Let's grab the right-hand side of the equation, LHS. QN. Okay. Let's go ahead and let's, for our own debugging sake, let's do LHS equals A. RHS equals that. Okay. LHS, RHS. Okay. And then let's make sure that this all works. Symbols not used, that's fine. For now, we're okay with that. We can go ahead and, if we wanted to, add or declare ignore sim for the time being. Okay, good. So now let's go ahead and rerun our equation list here. Okay. So now what we do is we check to see if um, how do we figure out if one of them is an equation here? That is the bigger question. Let's see. How did they figure it out here in solving equations? Solve arithmetic. Here we go. So what is this EXP operation guy do? Is defined somewhere. Ah, here we go. Type list LHS plus RHS, and then we've created the operation of the expression. Okay, so if so, let me try something here. exp up of exp LHS of ELT equation list 0. So we're trying to see if it's going to give us, it's not a type list. Perfect. So as long as I provide here, we're going to always assume that the first one, so whether it's LHS or RHS, the first one that contains the single unknown, that's the unknown that we need to return. So what we could do is we could say, not here, if, oh no, dang it, not if um oh, so actually we don't need to even do if, we can actually say when. No, go through this. If list p exp LHS of EQN, then find EQN So there's three cases. If the expression on the left-hand side needs to be did under the right-hand side to do it, then otherwise we need to check the symbol names and see if they're equal. All right. So we need to say first case is when symbol, our original case that we wrote, and symbol p I guess LHS, okay, and oh, actually it's going to be or. So if either the LHS is a symbol and string name equals symbol name, and we'll clean this up once we've actually, need to make things a little cleaner, like writing a function on this. But for right now, we're not going to handle that. So either the left-hand side contains this, okay, or and symbol p RHS this, and string equals symbol name RHS symbol name sim. So if either of these are unknown that we provided, then what we need to return is the actual equation. Okay. Now, this might not give you the whole equation, but we'll work our way up to it. Ideally, we should be able to actually go in and we could keep on recursing through it, and we may need to add the original parent that was passed in here, just so that we can keep that in mind. So that's the original equation. But again, we're iterating through this to actually get to this point. So now, do find equation exp LHS. Oh, what am I doing? Okay, we actually already got this earlier. Okay, LHS. Okay, else when list p RHS find equation RHS. Okay, compiled, no warnings. So let's see what happens here. And plus is not of type list. Interesting. Why is it saying plus is the problem? Find equation. Ah. So I must have accidentally done something here. Ah, got it. There we go. Okay, so I have to go and actually now handle this with the appropriate things. If EQN is a symbol, because we're treating this as a symbol here and a recursive symbol like that. This is shit. This doesn't work the way I expect it to. So 1 second. I'm gonna have to do one thing here. Let me change up this particular thing. Bring this back. Do this. And instead of saying find equation LHS or RHS, let me just make them into lists. Contain that. Of single elements. Done. There we go. So we're returning the original equation that we want to substitute, but we're not returning the other one. That's hysterical. Why? So there's something wrong with that LHS RHS print there. So what is it printing? It's printing LHS. What is the Let me see. This seems weird to me. Oh, do this. Aha. Okay. And I would like to know what now print sim of sim. I bet you it's a uppercase lowercase problem. Okay, so let's double check that. Aha. Okay, so it's not actually getting the symbol being passed in because I forgot to pass in the symbol. I forgot to pass in the symbol. My apologies, folks. Here, sim, 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 sim. Boom. So, let's see here. We have to do the same thing that we did before. Put that in there. Let's see what happens. Compiled and loaded. Let's see. Overhead, overhead. But it did not return it. So, and the reason is we're just calling the functions. That's the reason. Instead of actually doing return. Like, you see how we're doing return here? We need to actually go and do the same in these calls. So let's go ahead and do that. Oops, sorry. Return. Return. Okay. And I know what folks are looking at this, they're seeing a lot of imperative code writing. We could clean this up once I have a better understanding of how to get the general solution in. There we go. And now we're returning only part of the original equation because we don't have the parent here. So this is pretty simple. we could, in this case here, also add, we could get rid of this key here. Let's just say sim and parent. And in here, what we'll do is, in our base case, we just simply say if parent return parent, else return the equation if it's nil. So and we could certainly do when parent or something like that, but this is fine. And then what we'll do here is we do this, and we do LHS as the actual original thing. Else we do RHS. And again, this is only one layer. If we want to make this general, then naturally this is going to become a little bit of a problem. If parent. So you're saying parent is null here. Oh, that's right. Because I changed the signature. So now it's just overhead and say nil. And then we could see let's see what happens with here. Print parent format t parent expression tilde a tilde present. Do that. Let's see this. Parent expression is now. Ooh, wrong one. That's not what I wanted to do. The one that I wanted is the equation this was written in. This came from. Yeah, that's right. There we go. This is correct. Okay, let's try that. And now we're getting the correct thing. So now that we have the first hit, now I'm not grabbing everyone, I'm firing the first hit here. So this is only going to solve essentially the equations of the form that we have to do. So we need to have at some point generalize this, but I'm just getting the infrastructure in order to actually accommodate and figure out how to actually go in and solve the construction problem. All right, sorry, the original solution. And so okay. So let's go ahead and continue on here. Now that we have this, we need to go and obviously substitute. And we could probably do what we're doing here already with the substitute expression here. Okay. So let's see if we could do this. Substitute Let's see, new, which is going to be, so to substitute the expression, we take the expression, we find the location that it was returned in, and then we need to go in and replace it. Um, let's see here. Um, so let's see what happens when we call the function isolate, actually. Maybe isolate already grabs this. Isolate the lone x on the left-hand side. Assumes there is exactly only one x. Okay, got it. So once we solve this, we can actually call this guy and see if that works. Let me see something here. Got it. So okay. So we need to write another function here once we find it to replace the function. I mean, replace symbol with so defun substitute x var. I don't know what this substitute function does right now. Substitute new old in sequence. Oh, nice. Let's see if I could do this. So let's grab def param. We'll generalize this in a second here. LHS equals. There we go. EXP of this equation list. So our LHS is now overhead. Now let's also define our RHS to being the opposite of this guy. Okay, so now what we're going to do is substitute. Let's see if this works. LHS into RHS in the sequence ELT equation list 0. Let's see what happens. Okay, so we need to find the place where we need to substitute. So we need to return as part of the um, as part of the return statement, not just the parent equation, but the index into the parent equation that we need to go and replace with. Because these are all expressions. And this one is particularly a list of lists. So if we gave, for example, like this, we would see and just make sure that this is actually giving us what we're expecting. Interesting. It's not actually replacing it with it, which is interesting. Why wouldn't it not? This is a bit of a pickle. Let's see here. This is 10 times 40. And what we're trying to do is, oh, I wrote it wrong because it's new and old. The new is actually this guy, and the old is this guy. Oh, wait, what am I doing? There. Now it's working. I just flip the arguments. Okay. So we can actually do this in the same function without creating the expression. We actually, instead of doing find equation, we could just for each equation in the list, we can actually go and construct the actual new version that contains this. And then replace by constructing a new equation by doing make expr with the parent left-hand side, right-hand side, and so what we could do here is so create updated equations here. So once we have an equation, updated equation, here. So once we have an equation with one unknown, we could just go ahead and replace it. So we take the list of equations that we want to replace, the symbol that we want to replace, the new expression that we want to replace it with, and the original parent expr, so that when we go and traverse the tree, we can actually construct the final expression. Now, the one thing here is we need to know where in our list, so which side of the equation that we're actually replacing it with. See, because once we do this, becomes, for folks who aren't aware, if we just simply replace this now with the original equation, okay, so now what we do is we just simply say, okay, let's make mkexp xp op of elt eqn list 0. So that's the actually LHS is first. So our LHS is going to stay the same here. The op is going to stay the same, and then this guy is going to change. Okay, so now we have the new equation, right? So what we could do is we can actually say set f elt, and we can always replace this later on. I'm just showing you how we're essentially the approach that we can actually take, like in the REPL manually, and then we'll write the code for it. So this is now changed. So if we now go to equation list, you can see that the equation list has now the following. Okay, and now we have one overheads. And if we try to then solve this by doing solve equation list, and we have to provide another argument. Sorry, 3. Let's see what we did here in solve. Oh, we need to solve equations. We have to do solve nil. Let's see what we could do here. Still not able to actually solve it, even though we now have a correct. Interesting. Interesting. So even though we've corrected here, so there's a little more work that needs to be done here. It's probably not able to deal with commutativity. Okay. This is going to take a little longer than I expected because I have to actually solve um, the so the issue here is that even though this equation is more or less constructed the way we were expecting it to because of the fact that we now have one unknown. I'm curious if it's actually going to. Let me see if one unknown actually recognizes that there's only one unknown for this. Aha. So there's still an issue with it recognizing that it's one unknown. So what is um, the substitute expression that we've created here? It has to be that's weird. Why is it so we know for a fact that we've now constructed a new equation list of the form. I'm wondering if there's too many. So this is actually correct in that this is I'm able to actually see the expression here with the appropriate number of parentheses. So unknown p might be the problem. Okay, so let's see what unknown p. So we know that no unknown here on the left-hand side of exp LHS LT equation list 0 is true. All right, correct. So now let's try what it says for one unknown for RHS. It's nil. Even though ah, so the problem here is we have to also reduce this guy right now. It doesn't recognize that we need to reduce it. So if I went ahead and changed this into, say, 50 times running, automatically it will recognize there's one unknown. So we need to update one unknown to also handle the case where we might have these combinations, and then we need to be able to isolate them and then combine them. This is going to be a lot more work than we would have time for today. Okay. All right, folks. So the problem is, let's see how far we can get in the remaining 20, 30 minutes that we have here for tonight. And we'll continue on. I may do another episode later in the week once I actually attack this particular problem a little bit more in detail if we can't finish it off tonight. Um, for those who are still on, who's watching, thanks for joining. Um, just like and subscribe if you like our material, and please make sure that you follow along on our meetup page um, for upcoming announcements for talks. And while I'm working through this, if anybody has questions, by all means post it in the chat, and I will answer them as I address them, as I see them. 1 second here. Let's see where I am here. So let's see. Let's try. So we need to further construct yeah. So that's evaluating actually the expression, but we don't want to necessarily do that. Let's see if I can use isolate to actually go and attack this. Um, X would be running. Let's see what happens. Uh-oh, we're killing the Lisp. We have to start from beginning because it looks like it was not liking me trying to isolate the way it currently is written. So PAIP. Okay, so now let's go and let's set our package to being PAIP. There we go. Clear rebel. Okay. And let's try this again. Load this requires student. Okay. So we now have that all defined. Let's see here. We did this. We know our equation list is now back to where it was originally. And so let's make this easier on ourselves. Let's go and change this. Instead of doing 10 times running as the word problem was defined in the book, let's go ahead and do the simpler case where everything is in the same notation. Okay, this is a little contrived because we're trying to solve the immediate problem, but at least it'll give us something to work with the existing infrastructure, and then we can go and work our way into seeing what would happen. So now we have our new equation list, which everything is correctly done. And what we do is we can actually do Ooh, okay. This may be broken now because I actually updated the, okay, so let's see. Create, update equation. I think right now it doesn't actually do the substitutions yet. So overhead nil, and it just goes in and returns it. Right. So we need to go in and actually construct the actual equation that's going to be returned. But what we would need to do is you know what? That's actually probably easier. Let me try and see. So we could return the parent. Let me see what we do this. Let's say that we still call this find equation. Okay, now and instead of just the parent, we also throw the index into the sublayer. But again, this is also going to assume that there's only one sublayer. 0 or 1, right hand, left hand. But at least it will give us something to work with. Okay. For now, let's explore this one thing, which is what if we replaced what we did before, substitute new is going to be exp RHS of ELT equation list one for the old value here. Okay, this, 1, and the sequence is going to be exp RHS of ELT equation list 0. And as we did before, this is going to go ahead and create, oops, invalid arguments 2, 3. Hold on, I must have done something wrong here. Oh, right. There we go. So now we got what we need. so now we have our original equation there. So what we're going to do is we are going to go and check if this new equation is considered one unknown now. And it's still nil. Interesting. So there's a format here that's missing. Let us do one unknown. Let's try one more thing here, which is oh dang. That's not what I wanted to do. So it's not even liking that new equation that we created. Let's try this. EPSU EPW. Enter. We get our thing here, and you're saying that this is not being treated as one unknown. Right, because the fact that, again, this is the same problem that I was talking about earlier. This is not what I need to do is I wasn't trying to do this. So what I need to do is say isolate, and then here do isolate running. Hopefully it will recognize, and it does not. So, okay. Looks like we are out of time today. Tune in next time as we continue our expression. We're making small progress. We created now a new function that will appropriately find us the equation of the unknown. We're creating the new expressions. We have an approach to actually go and create the new expressions, but we need to generalize it. Additionally, we need to be able to then solve the actual equations, which we already can do once we've actually reduced it. So if we're able to actually reduce it into something that could effectively do, because if we do one unknown, just to show you how this might, the goal is eventually we're going to have to be able to get to running times 50, and it will be able to recognize that the one unknown is running, right? And today, because of the way it looks like, what we need to do is we need to probably, there's two approaches. One is reducing it, which we need to do anyway for solving the equation using the existing infrastructure, or we need to go ahead and somehow write the ability to do mathematical and arithmetic on expressions with one unknown, which I'm going to start debating in my head. I'm not entirely sure which approach would be easier to. I would assume that the actual thing is if we end up reducing it ourselves when we're constructing the expression, but I'm not going to confidently say that just because as I'm going through this, I'm still learning how we might end up writing this stuff. So next time, tune in so this way we can actually continue our project here. I'm hoping next week would be our last visit to this. We shall see. And then we'll start continuing on with Chapter 8. So I appreciate all you joining me tonight. I hope you have a good Monday evening. Thanks.